Hey everyone, what I'd like to do in this video is give you the preliminaries about surface area or surface integrals, and then we'll be able to jump right into examples when we get into class, okay? This is a really difficult concept to try and sort of conceptualize, but the computation of it becomes pretty easy once you see the formulas, okay? So I'm going to use the Khan Academy article for surface integrals to introduce this, and what I'd like to do is read this nice and slowly with you, so that you've sort of seen me talk through it a little bit, and then you're not just reading it on your own with no guidance, okay? So he starts with what we're building to. So he says, in principle, the idea of a surface integral is the same as that of a double integral, except that instead of adding up points, and I don't like the word points there, I kind of prefer to think of it as, not really adding up points, adding up little, in our case, like little chunks of volume, right? So he says, except that instead of adding up points in a flat two-dimensional region, you're adding up points on a surface in space, which is potentially curved. So what this means is that instead of us having like a surface that's z equals f of xy, and it's defined over some, rectangle in the xy plane, where we would be finding, volume over that rectangle, but underneath the surface. Now we're thinking of there's this surface in space. It might be defined parametrically, or it might be defined as a function z equals f of xy, and we're actually integrating over the surface. So the region over which we're integrating is not something flat in the xy plane, but it's rather some surface in space. And then where do we go from that surface? Well, the actual function that we're integrating, in other words, the function that's the work is being done on the integral is some f of xyz, or it's a function in 4 space. That's what makes this so difficult, okay? So let's review what we've done so far, right? So far, we've taken this idea of, here, let me draw this so this makes a little more sense to you. So where we've been up till now is that we've taken this idea of a region in the plane. You've got some blob, you've got some r, and over it lies this surface, right? And that surface is the f of xy, right? Z equals f of xy. And what we're essentially finding with a double integral, right? These are double integrals that we used to compute way a long time ago, was that we were finding the volume that lied under the surface but above r. And now I can't really draw it because what we're now going to do is we're going to take that surface as the bottom. It's like the surface is the r, and then lying above, and I use quotes about above because above in what sense if we're in 4 space, the surface now acts as the r, or the thing over which we're working, and the function that we're going to be working on is going to be w equals f of xyz. Okay, that might make a little more sense with how he explains things here. Okay, so the notation, don't worry so much about the notation yet. I'll clean all that up in a little bit, but you notice that the function we're integrating has 3 variables. We're taking tiny pieces of surface area as our ds. Not really sure why he uses sigma, our book uses s. Computing a surface integral is almost identical to computing surface area using a double integral. We just worked on that last class, except that you stick a function inside the integral. So f will need to be turned into u's and v's. Here he has s's and t's, but we use u's and v's. And then the d capital S needs to be turned into u's and v's as well, which is done by taking the magnitude of the cross product of the tangent vectors, and then we're able to integrate with respect to u and v. Don't worry so much about that notation. I don't love it. I'll show you my version of it soon. So he says, this is analogous to how computing line integrals is basically the same as computing arc length integrals, except that you throw a function inside the integral itself. So the arc length, right, if we go back to single variable or some work that we did, right, our arc length is the integral of 1 plus f prime of x squared, right? And that's kind of how we turn like a ds, right? What we're really integrating is let's go from a to b ds, little chunks of arc length. Well, that arc length ends up being that thing, okay? Or for us, it involved, I'm kind of mixing multivariable and single variable here, but I think you get the sense that of what he's trying to say here. He's trying to say that doing a a line integral is like doing arc length, except you have a function. You have this f of xy, which gets the that curtain idea. So if you understand double integrals and you understand how to compute the surface area of a parametric surface, those are things that we just did, you basically already understand surface integrals. It's just a matter of smushing the two intuitions together. I'll go over the computation of a surface integral with an example in just a bit, and we'll do that together as a class. But first, I think it's important for you to have a good grasp on what exactly a surface integral does. So he does a little refresher here on double integrals, which is kind of nice to see, right? So here, R represents some region in the xy plane, right? I already talked about that. That's some, could be a rectangle, could be some blob. And f of xy is a way to associate each point of R with a number. Typically, we think of that as the height of a surface, but here he shows two other neat examples. He said maybe R represents a metal sheet, and f of xy represents the density at each point. That's his picture on the right. Or maybe R perhaps represents a geographic region. He shows Australia here, and f of xy represents the temperature at each point. So that's no longer height. The double integral provides a way to add up, right, to go through that region and add up the values of f on the region. The idea of adding up points in a continuous region is vague, so he goes through this process of chop R into tiny pieces, and we remember this when we learned double integral, chop the region into little subregions, multiply the area of each piece, thought of as dA, so take your little base area, by the value of f at one of the points, which for us was a height, right? Then add up the resulting values. So that could get you volume if you had a surface. For his examples, if R represents a metal sheet, f of xy and f of xy is a density function, the double integral will give you mass, right? Because you're taking density, which would be like, what units is that in? Let me think. So density is like mass per cubic centimeter or something, right? So density is mass per cubic centimeter, and we're multiplying by cubic centimeters, and we just get mass when we add all that up. Or if R represents a geographic region and f of xy gives the temperature at each location, taking the double integral and the dividing by the area will give you average temperature. That goes back to these examples up here, which are kind of cool other applications of double integrals that we haven't really used yet. We focused a lot on volume. Okay, so now we'll move into what about integrals over curved regions, okay? So cool pictures here for the examples that make this a little more real. So he says, why stay so flat? This idea of adding up values over a continuous two-dimensional region can be useful for curved surfaces as well. What if you're considering the surface of a curved airplane wing with variable density and you want to find its total mass, right? So we're not just talking about a flat sheet, but we're talking about a surface, right, that does some kind of movement in space, and it's got variable density around the wing. Or what if you have the temperature for every point on the curved surface of the Earth and you want to figure out the average temperature? Well, the surface of the Earth certainly isn't flat, right? If we have that surface and we want to take an integral over it. So this time the function f, which represents density, temperature, etc., or might just represent some f of x, y, z, must take in point of 3 dimensions, since points on the surface live in 3 dimensions. The abstract notation for integrating a 3-variable function f of x, y, z over a surface is pretty much the same as the abstract notation for double integrals. So we see this show up again, okay? And this is called the surface integral, okay? So look at his process down here. He says, chop up the surface S into many small pieces. So if we go back to my picture, now if this thing here is the surface S, right, chop that into little small pieces instead of chopping the region R into small pieces. Multiply the area of each tiny piece by the value of the function f on one of the points in that piece. It's not volume though, right? Because f of x, y, z exists in 4 space, and then add up all those values. Okay, so actual computation we're going to do together in class. The last thing I want to show you is a copy of my notes from last year, which goes through this really nicely. And those are right here. Okay, so go back to old stuff, right? Think about a single integral, okay? So this thing is going to compute the area under f of x between x equals a and x equals b on the x-axis. But if f of x is 1, we just get the length of the interval, right? So now go up a dimension. This thing computes the volume under f of xy over the region R, okay? And if f of xy is 1, then we just get the area of R. And then finally, last chapter, we introduced the triple integral. This thing produces the hypervolume under, and unders in quotes, f of x, y, z over the solid E. And if f of x, y, z is 1, then we get the volume of E. So that's a whole kind of line of integrals, building one dimension to another. And there's a similar development with line integrals. So we had this line integral, which was the area of the curtain. You remember that picture, right? You've got a curve in the plane, and then there's a surface above it, and we're finding the area of the curtain that lies between the surface and the curve, okay? And this ds, remember, is a little chunk of curve, a little chunk of arc length. And to compute it, we turned f of x, y into having t's in the expression. We rewrote ds as the magnitude of r prime of t dt, okay? When f of x, y was 1, that produced the length of the curve, okay? So building up a dimension from that, we'll get there in 1 second. Before we do that, I want to reference the other kind of line integral we did. So we did a line integral with a little f inside, and we did a line integral with a big F inside, a vector field. And this produced work, right? So work, the lazy way of writing it is f dot dr. What we're really doing is f dot t ds, which means how much force is in the direction of the tangent vector all along the curve. And then to compute that, we're doing the real way to actually do the computation is f dot r prime of t dt, which we also saw in the form p dx plus q dy, which brought in Green's theorem as well, okay? So we had two versions of line integrals, one with a little f, one with a big F. We're also going to have two versions of surface integrals. So a surface integral is really just a higher dimensional version of a line integral. Notice how instead of having a single integral with a function of 2 variables, we have a double integral with a function of 3 variables. And the even more complicated part is, well, how we had a little f or a big F. Well, here we can also have a little f or a big F. And then as subsets of each of those, we can have the surface parameterized like we learned last class, or the surface written as z equals g of xy, where it's just an ordinary function. Okay, so here's where we're basically going to stop at this point. This is our notation that we're going to use and that our textbook uses. When f of x, y, z equals 1, we get surface area. Okay, to actually compute these, we would write f in terms of u and v. This is if we have a parameterized surface. And then ds, that little chunk of surface area, is written like we learned in the last class, the magnitude of r sub u cross r sub v, right? Those little tangent vectors, the magnitude of that cross product gives us the area of that little parallelogram. And now we can finally integrate with respect to u and v, or the reverse. If the surface is not parameterized, but is given as z equals g of xy, then we're going to write f in terms of x and y, and our ds then becomes that little chunk of surface area that we also learned last class, which is the square root of 1 plus the partial squared plus the other partial squared, okay? So far we've only looked at the case of a surface integral of a little f, and we'll practice this in class next time. Okay, thanks for bearing with me. I know that wasn't the cleanest video I've ever made as far as having everything polished, but hopefully you get some sense of what a surface integral is.